A crate P of mass 1.25 kgs is connected to another crate Q of mass 2 kgs by a light string. The two crates are placed on a rough horizontal surface, so we know that there's some friction there, and then a constant force F of magnitude 7.5 newtons acting at an angle theta to the horizontal is applied on crate Q. Clearly, right? The sketch demonstrates that. And then the crates accelerate at 0.1 meters per second squared to the right, and then crate P experiences a constant frictional force of 1.8, and crate Q experiences a constant frictional force of 2.2 newton. And then the first question, 2.1, state Newton's second law of motion in words, right? I'm definitely not going to do that. And then 2.2, let's draw a labeled free body diagram for crate P, right? So let's pay attention to crate P now. So crate P is connected to crate Q by a string, right? So there must be tension on crate P moving to that direction, right? And then because crate P is lying on a surface, we must have a normal force, right? But then not only a normal force, but even the gravitational force, right? So we should have Fg and the normal force there. And then we are also told that there is frictional force. So let's have a force opposing the motion, right? So let's have F at there. Why is the vector for the frictional force shorter than the vector for the tension, right? It is shorter because the crates are accelerating to the right, right? So the tension, the force of the tension is overpowering that force of due to the friction, right? So we must show that on our length of the vectors. I don't know if I don't know if the examiners are gonna penalize you if your FR is not less than the tension force, but yeah, it's supposed to be less than the tension force because they are moving to the right. We know that they're moving to the right because of that acceleration of 0.1. Anyway, stories 2.1, 2.3, I meant 2.3.1. Let's calculate the magnitude of the tension in the string, right? So we want the magnitude of the tension in the string. In 2.2, we were asked to draw a labeled free body diagram for crate P, right? So let's try finding the tension in the string by using crate P. If we cannot use crate P alone, then we will resort to also using crate Q. So let's try here and see what happens. So we're gonna say for P, right? And we underline it. Why are we doing that, right? It's for the sake of clarity. We're not all over the show. We're showing the examiner that we know exactly what we're talking about. So yeah, let's see what happens. So obviously we have F net equals to MA, being the second law of motion, right? So we start with the bigger force and then we subtract all the opposing smaller forces, right? So here we've already established that the tension is greater than the friction, right? So we must have tension minus all the smaller forces. We only have friction opposing, right? So minus FR being equals to MA, right? We're only considering the forces along the horizontal and not the vertical, right? So when I have tension minus, so the frictional force that acts on crate P is given to us is 1.8. So this will be equals to the mass, which is 1.25 multiplied by the acceleration, which is 0.1. So now the tension is going to be 1.25 multiplied by 0.1 plus 1.8, and that should be equals to 1.925 newtons, right? And just like that, we have the magnitude of the tension. And now let's calculate the magnitude of the angle theta. So the angle theta has to do with our crate Q, right? So now again, Q we underline for the sake of clarity, and we say that F net is equals to MA, right? We leave in the examiner with no doubt. So again, so for crate Q, we're gonna need a free body diagram first before we do this, right? So for crate Q, I'm just gonna draw it here, right? We have the force acting at an angle, right? And then we have the normal, obviously, and then we have Fg, and then we have tension acting and then we also have frictional force, right? So if we compute that, we're gonna have so we on the horizontal axis, né? We're on the horizontal axis. Since it's we're on the horizontal axis, we're gonna resolve F along the horizontal. If we want to resolve F along the horizontal on a flat surface, we say F cos of theta, and then we subtract all the smaller forces. So minus tension minus friction shall be equals to MA. So what is F? We know fully well that F is 7.5, and then cos of theta. What is the tension? The tension, we calculated it in 2.3.1, right? So here we're going to have 1.925, and then for the frictional force is given to us as 2.2. And this will be equal to the mass of 2 kgs multiplied by the acceleration, which is 0.1. So 7.5 cos of theta will be equals to 2 multiplied by 0.1 plus 1.925 plus 2.2, right? We're making cos of theta the subject to the formula. So now it should be easy to see that theta will be equals to cos arc of 2 multiplied by 0.1 plus 1.925 plus 2.2, everything divided by 7.5. Obviously this is more messy, right? It will be more clean if you put this in your calculator first, but yeah, I'm just gonna do what I feel like doing. So theta should be equals to 51.93 degrees, right? And that's how we solve that problem there. A ball is thrown vertically upwards from the top of a building of height 25 meters with a velocity of 12 meters per second. On its way down, the ball passes a door which has a height of 1.9 meters and then strikes the ground as shown in the diagram below. And just like we always do, we can ignore the effects of air friction, right? So the first question here is 3.1, which is saying that let's define the term free fall, right? I'm just gonna leave that for you. And 3.2.1 is saying that let's calculate the time taken for the ball to reach its maximum height, right? So let's do a bit of conceptualizing here. So we at the top of the building here, and then the ball is thrown up with some VI, which is equals to 12 meters per second, right? And then the ball goes up until it reaches some maximum height. At the maximum height, we know that we will have a VF, which is equals to 0 meters per second, right? And then what else do we have? We know the acceleration fully well. The acceleration is equals to minus 9.8 meters per second, right, squared. So now we have to decide on the direction. We take in up as positive, right? Hence acceleration is minus 9.8. And what we're looking for, we're looking for delta t. So we have this variable here. We have VF, we have VI, we have A. We're looking for delta t. Which formula can we use? Should be easy to see now that we're gonna say VF is equals to VI plus A delta t. So what is VF? We're saying that VF is 0. What is VI? It's 12 meters per second, right? So we put it as it is without a negative sign because we're taking up as positive, and then plus A, which is minus 9.8, right? Minus 9.8 multiplied by delta t. So now it should be easy to see that delta t will be equals to minus 12 divided by minus 9.8, right? And yeah, if you put that in a calculator, you should get a time of 1.22 seconds, right? Now we can do 3.22. So 3.22 is saying that let's find the velocity with which the ball strikes the ground. So again, we're going to conceptualize and we're going to look at the information we have and see how we can solve the problem. So we're looking for what? We're looking for the velocity, right? So we're looking for some VF, right? We have acceleration, we always do, right? And then what else do we have? So it's coming from the top of a building and then it goes down to strike the ground. So we have a delta y, right? Our delta y will be equals to minus 25. Why minus? We have taken up as positive. So the direction down it must be minus, right? So we have that there, and then we also have the VI. Let's not forget, we have VI that is equals to 12 meters per second upright. So now we have these variables. We have VF, VI, A, and delta Y. Which formula can we use? So we're gonna have VF squared being equals to VI squared plus 2A delta Y. So VF squared is exactly what we're looking for. VI is 12, and then 2 multiplied by A minus 9.8 delta Y minus 25, right? So here, if we take square root on both sides, we should get VF is equals to 25.1794 meters per second downwards, right? Downwards. Let's put the direction there. Now, the only question that is a bit tricky here, I think, is 3.23. 3.23, you have to be, you have to be extremely, sober to do this question. So we're looking for the time it took the ball to move from the top of the door to the ground. So let's come to a sketch. So the ball is coming from the top, right? And then we go to some maximum height, and then as we go down, we add the door at some point of time, and then we keep going down until we are on the ground, right? So we're looking for the time that it takes for the ball to move from the top of the door to the ground, right? From the top of the door to the ground. So now let's fill in the information we have and see how we can solve this problem, right? So here we have a VF, which is equals to 25.1794, right? And then here we also know the acceleration. The acceleration is obviously minus 9.8 meters per second squared, right? And then we have delta Y. We know the height of the door is 1.9 meters. So we have delta Y, and then what are we looking for? We're looking for the time it takes. So we're looking for delta T. So what we can do here, we can calculate the velocity at this point, right? When it's at exactly the top of the door at this point. If we calculate the velocity at that point, we're going to use VF is equals to VI plus A delta T. My favorite formula, right? It's pretty much straightforward. So let's calculate the velocity at that point so that we can use that simple formula. So to calculate the velocity at that point, we're going to do exactly what we did at 3.2.2, right? But the only difference here is that delta Y is not 25, but it is 25 minus 1.9, right? Think about it. I'm sure you're going to get it. So we're saying that VF is going to be equals to the square root of 12 squared, right? Plus 2 multiplied by minus 9.8. We're doing what we did in 3.2.2, right? But then instead of our height being minus 25, right, it's supposed to be 25 minus 1.9, right? But then because then we have a minus, we're just gonna add so that we can have a less delta Y, right? Think about it. I'm sure you're gonna get it. So plus 1.9 here, right? And if we compute that, we're gonna get VF is equals to 24.4287 meters per second downwards, right? So this VF that we have here is basically going to be our VI, right? For the motion from the top of the door to the ground. So now our favorite formula, we can say VF is equals to VI plus A delta T, right? We're looking for delta T. So if we solve this and make delta T our subject of the formula, we're going to get delta T is equals to VF minus VI divided by acceleration, right? So VF is the answer we calculated in 3.2.2, right? So that will be minus 25.1794 because we're taking downwards as negative and upwards as positive, and then minus 24.4287 everything divided by 9.8, right? So everything divided by 9.8. So we should get a delta t, which is equals to, here we should have a minus. Let's not forget that. So our delta t is going to be equals to 0.0. So yeah, I think we're supposed to round off to 2 decimal places. So that will be 0.08 seconds. And then, yeah, that's how you solve that problem. Obviously, there's other ways you can use to solve that problem, but yeah, I'm deciding to go with that one. 3.3, the last question. What does 3.3 say in here? So here, we have, let's draw a velocity time graph for the motion of the ball from the moment that the ball is thrown upwards until it strikes the ground. Use the ground as 0 reference. Clearly indicate the following on your graph. So let's just have our set of axes first. I'm just gonna do them with a free hand, right? So we just trying to get this over and done with. So we have v here in meters per second, and then we have the time in seconds, right? So we take in the ground as our 0 reference. Okay, fine. And then we must indicate the velocity at which the ball is thrown upwards. The velocity at which the ball is thrown upwards. It's thrown upwards at 12 meters per second. But let's indicate here that we take in up as positive still. So here at 12 meters per second, our ball is thrown upwards, right? And then it takes 1.22 seconds to reach the maximum height, of which the velocity is 0, right? So here, we must have a time which is 1.22. And then from there on, what happens? It changes direction, right? And now we have a negative velocity. So our graph should keep on going down. That line must be straight. The line must be straight. Let me make sure that it's straight. So we have a straight line going there until we reach a velocity of 25.1794, right? With a negative value. So we have minus 25.1794, right? That is the velocity at which we strike the ground, right? And yeah, I think this should be it. Trolley X of mass 1.2 kgs travels at 8 meters per second east and collides with trolley Y of mass 0.5 kg, which is initially at rest. And then the velocity time graph below shows the velocity of the trolley X before, during, and after the collision with trolley Y. And then yeah, we have a fancy sketch there. And then the first question, 4.1, which is saying, let's state the principle of conservation of linear momentum. We'll leave that for you. And 4.2, 4.2.1. So for 4.2.1, we're looking for the velocity of trolley Y immediately after the collision. So how can we possibly determine the velocity of trolley Y immediately after the collision? We are going to use the principle of conservation of linear momentum, because we know fully well that the sum of the momentum before a collision should be equal to the sum of the momentum after a collision, right? So what is the momentum before a collision? We're going to have the momentum of trolley X plus the momentum of trolley Y. And then after the collision, we're going to have the sum of momentum of trolley X plus the sum of the momentum of trolley Y, right? So if we calculate the sum of the momentum of trolley X, let's not forget that P is equals to M multiplied by V, right? We're going to have 1.2 multiplied by 8. So now we can see that we need to decide on a direction. So let's take direction to the east as positive, right? And then the trolley, the momentum of trolley Y, it is at rest, right? So we have 0.5 multiplied by 0, right? This will be equals to the momentum after the collision of X. We have 1.2 multiplied by the velocity. The velocity is on the graph, right? Because here, this is the velocity before the collision, during the collision, and then immediately after the collision. So we have 4 then. And then plus 0.5 multiplied by the velocity of trolley Y, right? So without wasting any time here, we're gonna say that the velocity of trolley y should be equals to, so we have this 1.2 multiplied by 8 there, so we're going to have 1.2 multiplied by 8, and then this, because we're multiplying by 0, is going to fall apart, right? And then minus this here, which is just 1.2 multiplied by 4, and then everything divided by the coefficient of Vy, which is 0.5. So if we put that in our calculators, we shall get Vy is equals to 9.6, right? We take in direction to the east is positive, so this will be 9.6 meters per second to the east, right? To the east. And now let's do 4.2.2. So 4.2.2 is saying that let's find the average net force that trolley X exerts on trolley Y during the collision. The average net force that trolley X exerts on trolley Y during the collision. We already know that after the collision, trolley Y is going to move to the east, right? So the direction of this net force should also be to the east, right? Irregardless of the sign we're going to get in our calculation, right? Because the sign is going to depend on which body you use, right? Are you using trolley X or are you using trolley Y? But then that shouldn't have an effect on the magnitude, right? So if we use trolley X, right? So we're going to say F net is equals to delta P divided by delta T. Let me explain why I'm using trolley X instead of trolley Y. The velocity of trolley Y, we calculated it ourselves, right? So what if that velocity is wrong and then we use it again, right? There's a good chance that that answer will also be wrong, assuming that there's no positive marking. So let's just stick to trolley X because we're going to be using the velocities that are given to us. So there's no way we can go wrong with the values, right? Momentum final will be 1.2 multiplied by 4. Minus momentum initial, which is 1.2 multiplied by 8, and then divided by the change in time, which I've indicated here in our graph, right? It happens from 20.1 to 20.2 seconds. So here we're going to have 20.2 being the final minus 20.1 being the initial. So if I just, put that in my calculator, let me see what I get here. I'm getting minus 48, right? But we've already said that we don't care about the sign, right? We know that it's supposed to be 48 newtons to the east, right? To the east. And yeah, I think that's it for 4.2.2. Let's see what we can do for 4.3. So 4.3 here is saying that let's determine if the collision is elastic or inelastic, right? And explain the answer by means of a suitable calculation. So what is the prerequisite for an elastic collision? So if a collision is elastic, then we need two things to be conserved, right? We need the momentum to be conserved and we need the kinetic energy to be conserved. So in 4.2.1, we calculated the value of y, assuming that momentum is conserved. So it wouldn't make sense if we calculate the momentums again, right? Because that's what we're assuming. We're assuming that the momentum is already conserved. So we're just going to calculate the kinetic energy and see if it is conserved, right? Yeah, so let's go ahead and do that. So we're going to say EK before and then calculate that and see if it's equals to EK after. So EK before will be equals to just the kinetic energy of trolley X because trolley Y was stationary. So we're going to have a half 1.28 and squared, right? So if I just put that in my calculator, I have a half 1.2 multiplied by 8 squared. And that is 38.4 joules, right? And then EK after, now I have a half 1.2 multiplied by 4 squared. Plus, this is for our trolley X, right? Plus the EK for our trolley Y. We have a half the mass, which is, what is the mass again? The mass is 0.5, so we have 0.5 multiplied by the velocity which we calculated, right? 9.6, and then we square that. So let me just put that in my calculator real quick and see what I get. So multiply by 0.5 multiplied by 9.6 squared, I'm getting 32.64 joules. So since, you know, EK before is not equals to EK after, then we deem this collision inelastic, right? Let me start by apologizing because the way I'm going to solve 5.4 is a bit gangster, but let's see what happens. So the question is saying that a 12 kg block is initially at rest at point A at the bottom of a rough inclined plane. So we know that we have frictional force. The block is pulled up the incline by constant force F acting parallel to the incline, so we don't have to resolve the force. The block reaches point B, which is at a vertical height of 4.5 meters above the horizontal, with a speed of 2.5 meters per second. See the diagram below. The first question, 5.1, says that let's define the term non-conservative force, and I'm just going to leave that for you. And then 5.2, we are asked to draw a free body diagram for the block when it is pulled up the incline, right? So let's go ahead and do that. So clearly there, when the block is being pulled up the incline, there's a force F, there's an applied force, right, which is acting parallel to the incline. But then because it's resting on a surface, we must have a normal force perpendicular to the surface, right? And then obviously we're gonna have gravity, right? So we're gonna have weight there, and then since the incline is a bit rough, then let's have frictional force. So we have FR there. Yeah, I think now we can solve 5.3. So 5.3 is saying that calculate the work done on the block by the non-conservative forces when the block moved from point A to B. So we know fully well that work net is equals to the change in EK, right? But then what is another way we can represent work net? Work net can be work done by non-conservative forces plus the work done by conservative forces, being equals to the change in EK, that is 1 over 2 VF squared minus VI squared, right? So we're looking for the work done by the non-conservative forces, right? So we're going to see so let's leave that as a variable. We're going to have the work done by the non-conservative forces plus the work done by the conservative forces, right? The conservative force that is acting there, which we are supposed to calculate the work for, is gravity, right? Since we don't have the length of AB, we're gonna use the height instead, right? So if we use the height, because gravity is gonna be pulling the object down as it is moving up, right? We're gonna put a minus sign there. So we're gonna have the force due to gravity, right? That is the mass multiplied by gravity, the weight, right? And then multiply by delta x, the height, right? The height is 4.5, right? We've already put a minus sign here, so there's no need for us to say cos of 180, and this is going to be equals to a half. The mass is 12, and then VF is 2.25. we square that to minus 0 squared, right? So now we can say that the work done by non-conservative forces will be equals to, so we have a half 12 multiplied by 2.25 squared basically, plus 12 multiplied by 9.8 multiplied by 4.5, right? So now it's just a matter of putting this in the calculator, and I'm getting 559, I meant 0.575 joules. Let's go ahead and move to 5.4. So 5.4 is saying that the same constant force F now moves the block at a constant velocity. So constant velocity, we know for the while that the work net is going to be equal to 0, right? Because the change in kinetic energy is going to be 0 if we have constant velocity across a rough horizontal surface from point B to point C. So we have friction also, force Fx parallel to the horizontal surface. So force F is still intact, right? And then what else do we have? The magnitude of the constant frictional force acting on the block while moving from point B to C is 42 newtons. Is 42 newtons larger than the magnitude of the constant frictional force acting on the block when it is moved from point A to B. And then let's calculate the distance from A to B. We're going to say that work net is equals to EK, right? The change in EK. But we know that the change in EK is supposed to be equals to 0 because it is moving at a constant velocity. So here, the work net is going to be the work done by the force applied plus the work done by the friction, right? Which is equals to 0 basically. But then we can go ahead and solve this way further, right? So if we do that, we're gonna get force applied minus the frictional force, right, multiplied by the distance they're traveling. What is the distance they're traveling? It is BC, right? Multiplied by BC being equals to 0. But this is what I'm going to do here, right? This frictional force that is here, we know that it is 42 newtons larger than the frictional force in 5.3, right? So if we call the frictional force in 5.3 Fx, right? So if we let that frictional force in, so let's write it down. Let's say we let in the frictional force in 5.3 be equals to Fx, right? If we do that, then Fa minus Fx minus 42 will then be multiplied by BC will be equals to 0, right? Clearly from our sketch, BC is not equals to 0, right? But then we don't even have to make that assumption. We can just say BC is equals to 0, or Fa minus Fx minus 42 is equals to 0, right? So Fa, this is Fx. What am I writing? Let's be very precise. This is Fx. So Fa minus Fx is equals to 42 newtons, right? We know that for sure. So we're saying that the force applied minus the frictional force in 5.3 is equals to 42 newtons. Let's go to back to 5.3 so that I can show you something. Here in 5.3, we ended up saying that the work done by non-conservative forces is equals to 559.575 joules, right? But then which forces are we talking about when we say non-consecutive forces? We're talking about the frictional force, which is Fx, right? And the applied force, which is Fa. So here we can change that and instead write force applied minus Fx, right? Multiplied by delta x. Delta x is AB, right? Multiplied by AB is equals to 559.575 joules, right? But then here we say that Fa minus Fx is equals to 42. So we can just replace this with 42. So we're gonna have 42 multiplied by AB being equals to 559.575. If we divide both sides by 42, we get AB is equals to 13.32 meters, right? Some learner decides to investigate the relationship between the observed frequency and the frequency of sound waves emitted by a stationary source. The learner moved towards the source at a constant velocity. So we have the velocity of the listener being constant, right? Let's call it x, and then the learner records the observed frequency FL for a given sound source frequency. This process is repeated for different frequencies of the source, with the learner moving at the same constant velocity for each time, right? The graph below shows how the observed frequency changes as the frequency of sound waves emitted by the source changes. And then we have a graph there which we're going to talk about in a moment. But the first question, 6.1. So 6.1 is saying that let's name the phenomenon illustrated by the graph. Question 6, grade 12 physical sciences. If the question says name the phenomenon, it's always Doppler effect, right? So that's the answer for 6.1. We have Doppler effect, right? Let's move to 6.2. So 6.2 is saying that name one application in the medical field of the phenomenon in question 6.1. So that's we can write ultrasound, right? That's one of the applications of Doppler effect in the medical field. And then 6.3, write down the type of relationship that exists between FL and FS as illustrated by the graph. We can see that they are clearly directly proportional to each other, right? As FS increases, FL increases. So we can say here that they are directly proportional to each other. Right? If you want to go further, you can even say that as FS increases, FL increases, right? But then yes, just 1 mark, so this will be sufficient. But then if for instance it was for 2 marks, then you would say that as FS increases, FL increases. Now let's solve the problem. 6.4. So 6.4 is saying that 6.4 in blue, not in purple. So 6.4 is saying that the gradient of the graph obtained is found to be 1.06, right? If the speed of sound in air is, so we have v of sound in air is 340 meters per second. Calculate the magnitude of the velocity at which the learner approaches the source. So we're given the gradient of the graph, right? And so what we're gonna do here, we're gonna look for the equation of the graph so that we can know what the gradient is and find a way to solve our problem, right? So we know fully well that in Doppler effect we have FL being equals to V plus or minus the velocity of listener divided by V plus or minus the velocity of the source, everything multiplied by the frequency of the source, right? In our graph we have FL being the Y, and then we have FS being the X. So this expression here will be our what? Yeah, just like you guessed, it will be our M, right? So if we can take that expression there, and then we can equate it to 1.06 because that's the gradient. So what are we saying? We're saying that V plus or minus VL divided by V plus or minus VS should be equals to 1.06, right? It's not me, it's the question. So now we can substitute our values and solve for VL, right? We're looking for the velocity of the listener. So that V, this V here is for the sound in air, right? So we're gonna have 340. So because we are told that the listener or the learner is moving towards the stationary source, right? Then you must have plus VL, right? And then divided by 340. The sound source is stationary. So we're just going to have plus or minus 0, which is just 0. And this will be equals to 1.06, right? 1.06 is the same as 1.06 divided by 1. So if we cross multiply here, we should get 340 plus VL being equals to 340 multiplied by 1.06. So here it should be easy to see that VL will be equals to 340 multiplied by 1.06 minus 340, right? So VL should be equals to 20.4 meters per second, right? And that's how we solve that problem basically. Now let's do the last problem, 6.5. 6.5 is saying that the investigation is now repeated with the learner moving at a higher constant velocity toward the sound source. Copy the graph above in your answer book and label it as A. On the same set of axes, sketch the graph that will be obtained when the learner is moving at a higher velocity. Label this graph B, right? So this one, they're saying we must label it A, right? And we must draw a graph for when the learner is moving at a higher constant velocity and label it B, right? So let's see what the consequences of a higher constant velocity will be. So we know that we have the gradient being equals to V plus VL divided by V plus or minus 0, basically, right? This is what the gradient of our graph is. But then now the learner is moving at a higher constant velocity, right? So it will be easy to see that if VL goes up, right, the gradient should also go up, right? So for your graph B, you have the same straight line, but then the gradient is just slightly steeper than that one when the learner is moving at a less velocity. So we're going to have our graph here, right? The gradient is just a bit steeper, right? Just steeper than A, and then we label it B. So let's see what the first is about. A charged sphere M is suspended from a ceiling by a light, inextensible insulated string. Another charged sphere N of mass 2.04 times 10 to the minus 3 kgs and carrying a charge of plus 8.6 times 10 minus 8 coulombs hangs stationary vertically below sphere M. The centers of the two spheres are 0.3 meters apart, as shown in the diagram below. And then, yeah, we have a fancy sketch there, as you can see. The first question, 7.1, Coulomb's law inverse. I'm just gonna leave that for you, right? We're going to start with 7.2. Let's state whether the charge on sphere M is positive or negative. Let's state whether the charge on sphere M is positive or negative, right? So let's look at what's happening here. We have sphere N, right? Sphere N, it's in the air, right? But we know fully well that there must be some gravitational force acting on sphere N, right? But why is sphere N not going down? That is because sphere N is being pulled up by sphere M, right? So if we say that sphere N has a positive charge of 8.6 times 10 to the minus 8 coulombs, right? Then sphere M here, which is pulling sphere N up, should have a negative charge, right? If sphere M had a positive charge, then sphere N should just easily fall off, right? What's happening here can only happen if sphere M has a negative charge, right? So 7.2, we're saying that sphere M has a negative charge. Then 7.3, we have to draw a labeled free body diagram for sphere N, right? We already have a body diagram. Now we need to just, make it free. So for sphere N, we're saying that we have FG, right? That is pulling it down. And then we have the electrostatic force due to sphere M pulling it up, right? They are balanced. So that is why sphere N is stationary. It's not moving up or moving down, right? It's just hanging in there. Now let's do 7.4. 7.4 is saying that let's calculate the magnitude of the charge on sphere M. Let's calculate the magnitude of the charge on sphere M. So in 7.3 we just drew a free body diagram. In 7.4 we have to determine the magnitude of something. Should be obvious by now, right? We're going to use that free body diagram we just drew in 7.3. From the free body diagram there, we can see that the electrostatic force Fm, right, should be equals to Fg, right? That is why that sphere there is neither moving up or down. So what is the electrostatic force? We know that we're gonna have K, Q1, Q2, everything divided by R squared being equals to Fg, right? So what is K? K is a constant, that is 9 times 10 to the 9, and then Q1, let's make Q1 the charge that we are given, right? So that will be 8.6 times 10 to the minus 8 multiplied by Q2, the charge we're looking for. So we have Q2 here, and then everything divided by R squared. Their centers are 0.3 meters apart from each other, right? So when I have 0.3 meters squared when equals to Fg is the mass multiplied by the gravity, right? The mass is 2.04 times 10 minus 3 multiplied by 9.8, right? So here, what we're going to do, we're going to jump straight into the answer, right? We're going to say that Q2 is equals to this term here that I'm just, copying. This term here divided by the coefficient of Q2. So this entire term here, basically, right? But without Q2. Yeah, without Q2. So this is what we say in Q2 will be equals to, basically. This is one term, and the denominator is one term. So if you put that in your calculator, you shall get Q2 is equals to 2.3247 times 10 to the minus 6 coulombs, right? Now let's do 7.5. So we have 7.5, 7.5.1. How does the electrostatic force that sphere M exerts on sphere N compare to that exerted by sphere N on sphere M with respect to the magnitude? So the magnitude is the same, right? The magnitude is the same. The magnitude is the same. The magnitude is the same. The only thing that is different is the direction, right? So I don't know if for 7.5.2 we can just write opposite. I don't know if that will be enough, but I'm assuming it will be enough because there's just one mark there, and we just know that the only difference is that the direction is opposite. Yeah, last question, 7.6. So let's do 7.6 real quick. So 7.6 here is saying that point X is 0.1 meters vertically below the center of sphere N, and then we have a sketch there. You can just see it on the sketch. Let's just solve the problem. Let's calculate the net electric field at point X. So we're gonna say that E net electric field will be equals to the electric field due to charge M plus the electric field due to charge N, right? So now we can say that E net is equals to that will be KQ divided by R squared, right? Plus KQ divided by R squared for the faint-hearted ones. But now let's go ahead and substitute. K is a constant, that is 9 times 10 to the 9. So what is the magnitude of the charge on sphere M? The magnitude of the charge on sphere M is 2.32 times 2.32 times 10 to the minus 6 divided by the distance between M and X, that is 0.3 plus 0.1 squared, right? But then now we have to worry a bit about direction here, right? Because M is negative and N is positive. So let's substitute M with its negative value, right? So M here will be negative, and then we'll substitute N with its positive value. So if we go ahead with that idea, we're gonna have plus 9 times 10. Now we're talking about the electric field due to sphere N. 9 times 10 to the 9 multiplied by 8.6 times 10 to the minus 8. Everything divided by the distance between N and X, right? So that is 0.1. So we have 0.1 squared. And if you put this in your calculator, you should get minus 5.31 times 10 to the 4, right? Assuming that I'm not making any mistakes with putting that in the calculator. But then it says, let's calculate the net electric field, not only the magnitude, right? So now we have to worry a bit about the direction. We know that the SI unit is newtons per coulombs, right? So let's look at our sketch here and then worry about the direction. We know that M is negative, right? And then we know that N is positive. As our answer here is negative, we can see fully well that our sphere M is overpowering our sphere N, so to say, right? So the direction of the electric field produced as a consequence of those two charges there will be towards M, right? 8.2, we are told that the reading on the ammeter is 3.5 amps, right? So we have I being equals to 3.5 amps, right? And then 8.2.1 is saying that let's calculate the total external resistance of the circuit, right? So now let's go to our circuit and do some analysis and see what's happening here. So if we look at our cell here, you will see that we have the positive terminal here and the negative terminal here. So the current flows from positive to terminal, right? It cannot bypass through the battery. It has to take the longer route. So the current is going to flow in this manner, right? Here we have a voltmeter, so it's not going to go there, right? And at this point here, right? At this point, the current divides, right? So when the current divides, a proportion of the current is going to keep going through this route here, and then another proportion is going to go down through this route. So because current has divided, we will know fully well that the total resistance in this path will be parallel to the total resistance in this path, right? And then here the current flows as one, so this 4 ohm resistor here is in series, right? So we are asked to calculate the total external resistance of the circuit, right? So that will be given by, so we have R external being equals to RP, the resistance in parallel, plus the resistance in series, right? Let's start with the resistance in series because it's pretty much straightforward. We're gonna have RS being equals to 4 ohms, right? And we're done with that. Now we can calculate the resistance in parallel. So this is how you calculate the resistance in parallel. We say 1 divided by RP is equals to 1 divided by R1 plus 1 divided by RQ, and so on, depending on the paths you have, right? But then this R1 here is not one resistor, it's the total resistance in one path. And then this R2 is not one resistor, it's the total resistance in a path, right? So here you can see fully well that we have two paths, the one with the 3 and the 2 ohm resistor, and the other one with the 1 ohm resistor. So 1 divided by RP is going to be equals to 1 divided by, so let's use this path here, right? So that will be 3 plus 2, the total resistance on one path, plus 1 divided by R2, the total resistance on the other path. What is the resistance on the other path? We only have 1, right? So now from here, we can just go ahead and say RP is equals to 1 divided by 3 plus 2 plus 1 divided by 1 to the minus 1, right? You don't have to think very hard when you get to that step. You can just do it like I'm doing it here, right? So RP will be equals to 0.83333 ohms, right? So now we can conclude and say R external is equals to 0.8333 plus 4 ohms, right? And this will be equals to 4.83 ohms. Yeah. And that's how we essentially solve the problem. Now let's do 8.2.2. So 8.2.2 is saying that let's calculate the reading on V1, right? So let me just remove these lines here. So it's saying that let's calculate the reading on V1. So if you don't know what V1 is going to read, then you're not going to be able to answer this question, right? So now you have to ask yourself, if the voltmeter is connected across the battery and current is flowing to the external resistance, what will V1 read? V1 will read V external, right? And V external is equals to IT multiplied by are external, right? That's how you find V external. If there was a switch somewhere and then that switch is open such that there's no current that is flowing to any external circuit, then V1 would be reading EMF. But then here clearly the current is flowing to the resistors in the external circuit, right? So V1 will read V external. So what is IT? We know that IT is 3.5. What is R external? We know that R external is 4.83, right? So I'm saying 3.5 multiplied by 4.83, and that's giving me 16.91 volts. Let's move forward and do 8.2.3. So we have 8.2.3. So 8.2.3 saying, how will the reading on voltmeter V2 compared to the reading on voltmeter V1? Choose from smaller than, equal to, or greater than. So we have V2, and how does it compare to V1? So let's go to our circuit. We've already established that V1 is going to read V external, right? And then let's look at V2. V2 is connected across this path that is in parallel, right? V2 is going to read VP, right? And V external will obviously be greater than VP, right? Unless if we didn't have this resistor here, then V external was going to be equals to VP. But then in this case, we have that resistor there. So V external is definitely greater than VP, right? So V2 is less than that reading on V1. So we can write smaller than here. And yeah, I think that's it. We can move to 8.3 now. So let's do 8.3. So 8.3 is saying that Elena concludes that the EMF of the battery is equal to the reading on voltmeter V1. 8.3.1 define the term EMF. Yeah, I'm gonna let you do that one. And 8.3.2 is the learner's conclusion correct? Choose from yes or no. So Elena concludes that the EMF of the battery is equal to the reading on voltmeter V1. That is not true, right? That is not true. So let's say no here, and then we're gonna do the explanation in 8.3.3, right? So define the term EMF, right? So EMF, right, is the reading across on a voltmeter across the terminal of the battery when there's no current flowing to the external circuit, right? Back to what I was saying, if there was no current flowing to these external resistors that we have here, then V1 would be reading EMF, right? But then in this case, current is flowing to those resistors, so V1 is not reading EMF, but it is reading V external, right? That's why 8.3.1 asks you to define EMF. If you know if you know the definition of EMF, then you're going to be able to answer 8.3.2 and 8.3.3, because they're just depending on whether you know the definition of EMF or not, right? Yeah, let's move to 8.4. So 8.4, there's already some lines there. So we have 8.4. Let me just erase those. 8.4 is saying switch S is now removed and replaced by voltmeter V2 as shown in the diagram below, right? So instead of switch S here, we have voltmeter V2. We had switch S here, right? But now we have voltmeter V2. How will each of the following change, right? So let's just analyze how the current will flow when we have a voltmeter there. So the current is still flowing from the positive to the negative, right? So it's flowing in this manner, right? But then here, the current is not going to divide because we have V2. We know that voltmeters have very high resistance such that negligible currents a negligible current flows to the voltmeter, right? So we just assume that all the current just ignores the path with the voltmeter, and we keep going. So here we're gonna keep going, and yeah, that's how the current is gonna flow essentially. So this 1 ohm resistor is not playing any part in this instance. So 8.4.1. 8.4.1 says, how will each of the following change the power dissipated by the 4 ohm resistor, right? So here you have to be very careful, right? Because there's 3 equations for power, right? in electric circuits. So I'm gonna use P is equals to I squared multiplied by R, because if I use a formula that has V, then I have to calculate V for when we had the switch S, and then calculate V for when we don't have a switch S, right? And that's just too much work. So I'm just gonna take power as I squared multiplied by R. This just makes our life extremely easy. So yeah, let's analyze what's happening here. So the resistance of the 4 ohm resistor will still be the same, right? Will still be R. So here we are only worrying about the current. If the current has increased, then the power dissipated would have also increased. If the current had went down, then the power dissipated will also go down, right? So let's analyze whether the current goes up or goes down when we have V2 there. The current is going to go down, right? Because let's not forget that I is equals to V divided by R, right? So clearly, when that 1 ohm resistor is no longer in play, the resistance is going to go up, because all those 3 resistors, they're now in series, right? Resistance was initially 4.833, but then now the resistance is 3 plus 2 plus 4, which is equals to 9. So we can see that the resistance has increased. If the resistance has increased, then the current has went down, right? So the power dissipated here should be less than, right? Should have decreased, because initially we had a greater current, but then now current has went down. So here let's have decreases, right? And then 8.4.2, the reading on V1. The reading on V1 is going to increase, right? And then we're going to explain that in 8.5, right? So yeah, so it's one of those questions, 4 marks, you know it's gonna be there, this question, and you must be prepared for it. So what's going on? We know fully well that in our electric circuit, EMF is equals to IR plus I multiplied by the small r, right? V external and V internal, right? So we're saying that R external increased, right? When we put a voltmeter there. When R external increases, what's going to happen? The current is going to decrease, right? We know that fully well. But what will be the consequence of the current decreasing, right? So we're going to have EMF being equals to I multiplied by R plus I multiplied by the small r, right? When the current decreases, this V value here is going to also decrease, right? V internal is going to decrease when the current decreases, right? Because small r doesn't go up or go down, right? It's the consequence of the material used on the battery. So we're saying that V internal is going to decrease. But then at the same time, EMF cannot go up or down. It remains the same, right? So if we're saying that V internal decrease, then we need V external to increase, right? And then V in external is being read by voltmeter V1, right? So that is exactly why we're saying that the reading on voltmeter V1 is going to increase. You will have to excuse the way my question paper looks here, but yeah, it is what it is. So the first question, 9.1.1, is saying that let's name the component in this generator that ensures that the induced current in the external circuit is in one direction only. Name the component in this generator that ensures that the induced current in the external circuit is in one direction only. That is the split ring that we have here, right? So 9.1.1, we have split ring. Now let's do 9.2.2. 9.1.2. 9.1.2 is saying that is the direction of the induced current from X to Y or from Y to X, right? I will let one of you let me know in the comment, and then I will pin that comment, right? So please leave a comment there and let me know whether the induced current is flowing from X to Y or from Y to X, and why you are saying so, right? Now let's do 9.1.3. So now 9.1.3 is saying that a maximum voltage of 90 volts is generated when the coil is rotating at a frequency of 20 Hz. Let's write down the time taken for the coil to complete one rotation. So we have frequency being equals to 1 divided by the period, right? Grade 10. So if we rearrange this formula, we should get the period being equals to 1 divided by the frequency. So this should be 1 divided by 20. And if I put that in my calculator, I'm getting 0.05 seconds, right? So that is the time taken for the coil to complete one rotation. Let's move to the next question, 9.1.4. So 9.1.4 is saying that the coil starts rotating from the initial position as shown in the diagram above. Sketch a graph of output voltage, current versus time for one complete rotation of the coil. Indicate the maximum voltage and the relevant time values on the graph. So let's sketch our axis here and see what we have. So we have our y and we have our x. So on the x we have time in seconds, and then on our y we have voltage in volts, right? So we can just leave that like that then. So we only want one complete rotation. So this is DC, right? So we shouldn't see anything like this manner because it's DC. It should look like this, right? So we change direction, we go up again, and we have one complete cycle. So this time here should be 0.05, right? Because in 9.1.3 we say that it takes 0.05 seconds to complete one rotation, right? What else do we have to indicate here? We must indicate the maximum voltage. We must indicate the maximum voltage. So on the y-axis here, we're gonna write the maximum voltage is 90 volts, right? So we're gonna have 90 volts here. So this 90 volts will be in line with that part there, just like I showed you with my line. You can see my graph is a bit, sloping up, but yeah, it should be a straight line. And then 9.2, the last question, the wall sockets supply RMS voltage and current. Okay, 220 volts AC voltage is applied from a wall socket to an electric kettle having a resistance of 32 ohms. Let's calculate the average energy dissipated by the kettle in 2 minutes. So we have the power being equal to the work divided by the time, right? If you want to find the energy dissipated, you say the work equals to the power multiplied by the time. So the power can take different forms, right? Depending on what you have. Here we have the voltage and the resistance. So the power will take the form P is equals to V squared divided by R, right? So the energy dissipated will be V squared divided by R multiplied by delta time. So what is V? V is 220 volts. So we square that. R is 32. And then the change in time is, what is the change in time? Change in time is 2 minutes. So we have 2 multiplied by 60. Now, if I put that in my calculator, so I have 220 squared divided by 32 multiplied by 120. And I'm getting 181,500 joules. Light is incident on the cathode of a photoelectric cell connected to a battery and a sensitive ammeter as shown below. And then 10.1, so we have 10.1 here saying that what conclusive evidence about the nature of light is provided by the photoelectric effect. The photoelectric effect proves that light can act as a particle, right? So that's 10.1. The photoelectric effect proves that light can act as a particle. Now let's do 10.2. So for 10.2 here, The first question is saying that let's define the work function, right? So I'm just going to leave that for you. You're going to define the work function, and I'm going to go ahead and do 10.3. So 10.3 is saying that light of frequency 5.96 times 10 to the 14 hertz. It's shown on the cathode. And then let's calculate the maximum kinetic energy of an electron ejected from the cathode. So we're given the work function, we're given the frequency incident. So if we have the frequency incident, then we can calculate the energy, right? What else do we have? That's all we have, and we need EK max, right? So we know the formula we're going to use here. We're going to say that the energy is equals to the work function plus EK max plus EK max. But what is the energy? The energy is given by H multiplied by F, being equals to the work function plus EK max, right? So if we make EK max the subject of the formula from just the get-go, we're gonna get H multiplied by F minus the work function, right? So what is H? H is a constant, that is 6.63 times 10 to the minus 34, and H is also given to us, that is the frequency of the light, right? 5.96 times 10 to the 14 hertz minus the work function, which is 3.42 times 10 to the minus 19, and that should be equals to 5.3148 times 10 to the minus 20 joules, right? EK max is in joules. So let's do 10. So we're at 10.4 already, so let's do 10.4 here. So 10.4 is saying that the ammeter registers a constant current. So we have some I, which is equals to 0.012 amps, right? Calculate the minimum number of photons of light that strike the cathode in a 10 seconds period. So we have delta T being equals to 10 seconds. So we know fully well that the current is the rate of flow of charge per unit time. The rate of flow of charge per unit time through a point or a region, right? So what are we saying? We're saying that I is equals to the charge divided by delta T. But what is I is given to us is 0.12, and then what is the charge? Let's look for the charge. So it seems like what we have to start with here is looking for the charge, and then divided by, this is 0.012, not 0.12, so 0.012 divided by the time. The time is 10 seconds, right? So if we cross multiply here, we're gonna get Q being equals to 0.12 coulombs, right? So we have Q, which is 0.12 coulombs. Let's not forget our aim here. The question is saying, let's calculate the minimum number of photons of light that strike a cathode in a 10 seconds period, right? We know fully well that in photoelectric effect, one photon ejects one electron from the metal surface. So if we calculate the electrons here and we find that the electrons are, we have 100 electrons, then that means that the minimum number of photons is also 100, right? Because we need one photon to eject one electron. So let's calculate the number of electrons, aka the number of minimum photons required in this instance, right? So how do we calculate the number of electrons from the charge, right? You say that the number of electrons will be equals to the charge divided by the charge of an electron, right? So let's just put small letter q there. So if we do that computation, we're gonna get 0.12 divided by the charge of an electron. So what is the charge of an electron? The charge of an electron is 1.6 times 10 to the minus 19. So our answer here should be 7.5 times 10 to the 17 electrons, right? So the minimum number of photons is also equals to 7.5 times 10 to the 17. The last question, 7.5 is saying that the intensity of the incident light is now increased How will this change affect the reading on the ammeter? Choose from increase, decrease, or remain the same. Explain the answer. So the reading on the ammeter will increase, right? The reading on the ammeter will increase if we increase the intensity. So let's say we had 3 photons that are going to be incident on the surface of the metal, right? If we increase the intensity, then we're increasing the number of photons that will be incident. So let's say, from instance, we had 3 photons initially, and now we have 6. And we know fully well that each of those photons will eject an electron from the surface of the metal, right? And when an electron is ejected from the surface of the metal, that is current. Current is going to increase, right? I is equals to Q divided by T,